Hi, this is Danny Tang. I am doing probability and stochastic homework 2, problem 2, which asks us to, in part A, asks us to draw the distribution function 1 minus e to the negative alpha x times the unit step shifted by c. So we can look at this in two parts. First, this part, and then the unit step. And we know that 1 minus e to the negative alpha x looks like this. When it's less than 0, it's negative. When it's positive, it goes to 1 as x goes to infinity. So this is what 1 minus e to the negative alpha x looks like. And then we look at the unit step but shifted by c. We can look at this two ways. C could be positive or C could be negative. And when it's positive, it looks like this. And when it's negative, it looks like this. But we know that in 1 minus e to the negative alpha x, when x is less than 0, it's negative. So we know that C has to be positive. So then the distribution function will look like this. And this is C. We pick an arbitrary value, and so this is 1 minus negative alpha x goes to 1, and then the unit step from C. So it's a little bit curved and it goes towards 1. So this is what the distribution function looks like. And in part B, it asks us to find and draw the probability density function, which is the derivative of the distribution function. And when we do the derivative, it comes out to be 1 minus e to the negative alpha x times impulse function shifted by c plus alpha e to the negative alpha x times unit step shifted by c. And in the problem, we're given this sampling property of impulse functions, which says h of x times impulse shifted by a equals h of a times impulse shifted by a. So when we apply this to this part of the function, we get the probability density function as 1 minus e to the negative alpha c, since we replace the x in the impulse function by the shifted units in the impulse function. So this part remains unchanged. So this is what the density function looks like. When we graph it, it will look like this at C. The impulse function is just a line, and it goes towards infinity. And so this is 1 minus e to the negative alpha c times impulse shifted by c. And then this part would be this, alpha e to the negative alpha x unit step shifted by c. So this is what the graph looks like. And we want to prove that this is a valid density function. To find that, we have to take the integral of this density function, and it has to equal 1. So we can do this by two parts again. Looking at the impulse delta function, we know that the area of this is just 1 minus e to the negative alpha c, this in line. And then when we look at this part, we take the integral from c to infinity because it's shifted by c find the area under here. So this would come out to be negative E alpha x. And the limits are c to infinity. And we can see that when e goes to negative infinity, it's 0. And so we're left with this. This is the area under the curve here. So we add the two areas of the delta function and the area we just found. Minus e to the alpha c. So this is the area of the impulse function. Plus e to negative alpha c, which is area under the curve. These two cancel out. You see that this is 1. So we can say that f of x is a valid PDF.